Okay, so what we're going to end up doing now is spend some time working on a specific type of organized counting called permutations. Okay, and there's a bit of terms that I'll use all the way along through here, but I kind of want to define those, even though we kind of talked about what they were a little bit last video. Permutations, okay, have things that we arrange in order, okay? And the things that we arrange are called elements. Now, technically that comes from a term that means elements of a given set. Okay, and a set is just a collection of items that maybe has something in common, or at least something that you're talking about. And so you always have all these elements. These are things that you're arranging. So if you remember from last lesson, we had flags that we were arranging in different orders to make different messages, or we were arranging the chess pieces in different sort of orders, first place and second place, or first choice and second choice, or it was the outfit, or the trip to Egypt, where we were arranging flights and things in a specific order. Okay, so these things have elements. Okay, and these are elements are things to arrange. Okay, and they are in positions. Now we'll come to understand this and derive this as time goes on, but this could be like first, second, third, or left, right, middle, or I don't know, lane 1, lane 2, lane 3. And these all go dot dot dot. You don't have to have 3 of them. I'm just listing them as 3s. Or you could do president, vice president, treasurer, secretary, whatever. These are all different positions, and so if you take those elements and you put them in different positions, then they have sort of different. If it's president, vice president, treasurer, secretary, like student council, or first, second, third, that could be like how people finish in a race, or left, right, middle, that could be how they're positioned for a photograph, or I don't know, in a classroom. And then lane 1, lane 2, lane 3, lane 4, that could be positioning whether you're running a race or whether you could be doing any type of thing, just walking through a door, whatever it may be. Okay, so let's look at these situations and use them to model this situation. Okay, first of all, ignore the 2.3 if you're a night school or summer school student, but if you're a day school student, then 2.3 is a section that we use with a newer textbook. Okay, depending on whether we're online or whether we're back in school. Hopefully back in school. Anyway, 6 racers are set to run the 100-meter dash. Okay, so these would be the lane type situations. How many different ways can the assigned lanes line up for the race? So we're going to consider the possibility of a tree diagram. This would start with one of the 6 racers being assigned lane 1. If you do it in that order. It doesn't have to be in that order, but it's easiest. And then, the rest of the racers you have to choose to add in to lane 2, and then to lane 3, and then lane 4, and lane 5, and lane 6. Okay? So 6 racers are going in 6 positions because they all have to run the race. So the first choice is going to be, it's going to have 6 branches. I'm just going to call the racers A, B, C, D, E, and F. Okay, and that's going to be lane 1. Okay, or if you prefer, lane 1. Okay, that's a lane 1 choice. And then from there, what we're going to do is we're going to take the other 5 racers and put them in lane 2. So this next one's going to be the lane 2 branching. And I'll branch off of A, and I'll go 1, 2, 3, 4, 5. That would be B, C, D, E, and F because we've used up A. Or here, 1, 2, 3, 4, 5. And that would be A, and then skip B, C, D, E, F. But what you'll notice is, of course, I'm kind of getting crowded here for my 5 here, and my 5 here, and so on and so forth. So we're hoping there's going to be a better way for me to do it. But if you notice that there's 6 possibilities here, and then 5 possibilities here, and then 4, and so on and so on and so on. So what we end up doing when we do this is a little bit simpler of a scenario, kind of like with the chess pieces, where once you take one out of the bag, you don't have any more of that chess piece available, so there's one less chess piece. Or if it's the flags, taking them out of or using them in the first spot for the message. If you wanted to do a 4 flag message, you start with 4 flags, then you go to 3, and then 2, and so on. So we're going to do the same idea. So if we start in lane 1, there's 6 people that could go in that spot. once we put a person in that spot, whoever it is that we choose to put in that spot, there's going to be 5 people left that could go in this spot, and then 4, and then 3, and then 2, and then 1. And what you would say to yourself is, well, I don't know, what if I decide to fill lane 4 first? I know that when you race, some lanes are better than others. Maybe the center lanes are the ones that are sought after. I'm not a track person, so I don't know. If that's the case, then you could still do the same idea. Okay, and you'll find out why this is mathematically equivalent, and of course important that it's mathematically equivalent, because it shouldn't matter which position we fill. So let's say lane 3 is the best one, so 6 people will choose that particular lane, and then there's 5 people left, so they'll choose maybe lane 4, and then I don't know, 4 people will choose lane 2, because that's the next best, and then 3, and then I don't know, 2 and 1. And so then it doesn't have to be in that order, but the whole point is, what we do remember with our fundamental counting principle is this is a race setup. So that means we have someone in lane 1 and someone in lane 2 and someone in lane 3 and someone in lane 4 and someone in lane 5 and someone in lane 6. So what we end up doing is we end up multiplying all of these, and that's why the order doesn't matter. You can go 6, 5, 4, 3, 2, 1, which is the easiest way to do it, because it's just step by step from left to right like we normally read. Or you could just sort of put them in whatever type of order you want to, but in the end you only multiply by 6 once, and 5 once, and 4 once, and 3 once, and 2 once, and 1 once. Now, to model after permutations, we would kind of tend to go in order. Okay, but that doesn't have to happen that way in reality. It's the easiest way for us to do it. We start from left to right and we go 6, 5, 4, 3, 2, 1, multiplying them all together. And actually ends up being a pretty sizable number. 720 different ways in which those racers could be lined up if you just line them up maybe randomly and all those different things. If they got to choose, well, then it's a different story. Okay, and obviously people would tend to clump in different positions, and I don't know if people who race in the same team want to be side by side, or rivals want to be side by side so they can see each other as they're running their race. I don't know, but the point is if it's all random, there's 720 different ways to line those people up. And of course you see that drawing a tree diagram is just going to be insane. Okay, now in the good copy version of it, okay, where it looks a little bit better, you can have a look there and see that I've actually followed through from D, 5, and then 4, and then 3, and then 2, and then 1 in that particular situation. Okay, and as a result, those are all the numbers of different chains that I have, or branches that I have in that process. Okay, I know it looks like that I have 2 here, but if I choose C, then the other one's going to be E. If I choose E, the other one's going to be C. Okay, and so again, these are all associated with the different lanes, and so we have this 6 times 5 times 4 times 3 times 2 times 1 calculation, again, because our fundamental counting principle centers on the whole idea of and, or. In this case, I'm choosing lane 1 and lane 2 and lane 3 and lane 4 and lane 5 and lane 6 to fill, okay, for a particular race. All right, so in the above example, okay, or maybe if I want to have an above example, there's the above example. In the above example, each athlete is a unique, what we call, element. Okay, each person is a unique element. Okay, and they're all arranged into lanes or positions. Okay, so these are elements in different positions. Okay, I've got 6 elements and I'm putting them in this position, and then 5 elements in this, and so on and so on and so on. Okay, where one element's location relative to the other creates a distinct arrangement, okay? And that distinct arrangement, because it's the same 6 people who are running in the race, but it's where they're situated compared to each other, left and right and front, and, or sorry, left and right, or all the way to the edge, or in the center, or on the other edge, okay? And so we call these permutations, okay, where we take n elements, n for number of elements, and arrange them into positions. Now, we don't use a p for positions because the p is what we use for the permutations, so we call them r positions. Okay, to give a number of different distinct arrangements. Okay, the formula, and there's actually a formula for this, okay, to give a number of, the formula for that summarizes this situation is abbreviated NPR, okay, where N is the number of elements, in this case it would be 6, and for our racers, and then P, and then there's going to be how many positions? Well, there's 6 positions. Now, I can plug that into my calculator if I want to, or I can do it by hand. If I do it by hand, 6p6 is going to be n factorial, which is 6. There's 6 racers, or 6 elements. and then n minus r factorial. So that's going to be 6 racers minus the 6 positions. Okay, so 6 factorial. You don't even know what a factorial is yet, but I'll show you what that is. 6 factorial over 0 factorial, or 6 factorial. Now 6 factorial is just 6 times 5 times 4 times 3 times 2 times 1. The weird one is the 0 factorial. 0 factorial actually, strangely enough, is the number 1. Okay, because you never get down to 0. Okay, if you got down to 0, then any factorial, or even went into the negatives would oscillate back and forth. And if it went into the 0, then of course 0 times anything is going to be 0, and that's not going to work out for you. Okay, so we would abbreviate that as exactly what we saw in our lane arrangements. Okay, 6 times 5 times 4 times 3 times 1. Or another way to write this is 6 factorial. Okay, so that is sort of the idea of a permutation. Okay, and that's what this little exclamation mark means. Now, there's a little video that you're going to have in this particular section. It shows you how to calculate things. It shows you how to calculate factorials in your calculator. Okay, on this calculator, and every calculator is different, I have a couple of buttons that are really useful. In fact, I actually have an NPR button right here. Now, it's going to be difficult for you to see, and of course, in every calculator is different. If you have this calculator, I guess it's quite useful. But either way, if I wanted to go 6p6, I would go 6. And then I will go to the second function, because if you notice that the NPR is in second function right here, you probably can't even see it on the video. So I don't know, even if you can zoom in, maybe you get lucky. But 6, and then I would press NPR, and you'd see the little P that's there. Okay, that's the NPR, and it's looking for the next thing for me to enter, which is going to be 6 as well. And that would be 6p6 or 720. You could also do 6 factorial if you wanted to. So you would go 6. And then the factorial for me in this calculator is all the way over here. See, even I had a little look at this, my daughter's calculator. Second function, okay, and then we would go for the 4. And notice how it's 6 and then an exclamation point. And then you would press enter, and it would give you 720. Okay, so that's how you would do those calculations. But I have a video for you that sort of shows you how to do those types of calculations. So make sure you watch that one. It's like a, I don't know, 2 or 5 minute or 8 minute video. It's nothing. It doesn't take much time at all. It's not like a whole lesson. Okay, so let's look at our next example. How many different 5-letter words, and I put, ear bunnies or quotes, words, and the reason why is, of course, only certain arrangements of letters can form a word in whatever language it is that you're speaking, okay? And so, of course, when I say words, I really mean arrangements of letters, okay? Because arrangements of letters are kind of like words. Now, most of them will be nonsense, but that's not the point. The point is that how many different ways can we arrange those letters randomly? The letters aren't necessarily what we're doing here. We're not randomly arranging letters to see if a kid can spell something. A 1-year-old can be playing with letters and can spell something magically, or it's 1,000 monkeys and 1,000 typewriters trying to type a greatest work of art, okay, or a greatest novel. But the point is that we want to look at arrangements in positions, and that's what we're doing. So when we look at this, we have 5-letter words in a toddler form with the letters A, B, C, D, E. So first of all, we have 5 elements. I just do ELE for my elements, okay, and that's A, B, C, D, E. So there's 5 different things, and we're going to arrange them into 5-letter words, which means we have 5 positions. So what I do is I can go straight to the permutation if I want to, because I could make that 5p5. But what I like to do is I like to do sort of to visually structure something, and it's going to be a really important process for you to do it. So I outline the 5 positions that exist. Okay, and then I start filling the positions with the elements that I have. In the first spot that I fill, I put 5 because I have 5 elements to choose from. Once I've put 1 in here, then there's going to be 4 choices, and then 3, and then 2, and then 1. And that, of course, equals 5 factorial. Or, like I said, you could jump straight to this definition. If we have 6 elements and 6 positions, it's 6p6. If I have 5 elements and 5 positions, it's 5p5. Plug that into your calculator, or plug in 5 factorial, or do 5 times 4 times 3 times 2 times 1, and you will get 120. So that would mean that there's 120 different ways or words that you could possibly form. Okay, with these 5 letters A, B, C, D, E. Okay? And that's sort of the whole idea, okay, that we're looking at here. Another example right here, so we can sort of start to cement our understanding, is how many ways can a 10-person volleyball team line up for a photo? Well, we've got 10 people in the volleyball team, okay, so that would be 10 elements. and they're lining up for a photo. I'm assuming they're all lining up. No one's escaping the photo. So it's going to be, sorry, 10 elements, excuse me, in 10 positions. Okay? And then, of course, the number for that would equal 10p10 if you wanted to do straight to the permutations definition, which is cool. Okay, and you can do that. But again, I like to map this out so you can actually, I'm a visual learner, so I would go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And go 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Of course, that takes a long time. That's also 10 factorial. And again, just to review how we would do that in our calculator, I would go 10, second function, and that's my NPR button. There's the P. And then 10. Okay, it's a huge number. Okay, that's going to be 3,628,000. Okay, so lots of different ways. Oh, sorry, 8,800. Oops. Okay, that's a lot of different ways. Or another opportunity for us to do the 10 factorial. Second function, and then there's my n factorial button, or sometimes you'll have an x factorial. See, there's the exclamation mark. And then there we go. We get the same number, right? Same number. Okay, or I guess you could if you wanted to, although, so, you know, doing 5 times 4 times 3 times 2 times 1 is fine. And again, that's the implication in here. When I put them side by side, they are going to be multiplying because, again, remember, with the fundamental counting principle, I'm going to be putting one person in this spot and then putting one person in this spot and then one in this and then one in this and then one in this. So they're all ands, and so we're all multiplying. Okay, and a factorial is a multiplication and a permutation is a multiplication, entirely operation. Okay, so if I am going to do this last a little bit, most people aren't going to want to do this, but you go 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, and hope that you didn't make a mistake. Okay, and yeah, you get 3,628,800. So eventually for your calculations, you're going to want to steer towards this or this. But either way, it's sort of the idea that you can do them in multiple ways, and it is good to visualize and see things, because once we start doing some fancier things, and we are going to do fancier things, then this arrangement is going to be really useful for us to do our problem solving with. Okay, so that's another, arrangement of 10 people in 10 positions. Okay, so let's move on and look at some more examples where we start to get more specific. Okay? All right, so how many ways can the same 10-person team, okay, so we still have 10 elements, and I'm assuming they're lining up for a photo, so in 10 positions. Same 10-person team line up for a photo if the two captains must be beside each other. Okay? Now, this is a bit of a weird situation, okay? Because what ends up happening is, if the two captains are side by side, or the two captains are side by side each other, okay, then well, I'll map it out first of all. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so if there's two captains that are side by side for each other, then maybe the captains could be here and here. Captain, right? Or we could go captain, right? Or, anywhere along the way, as long as they're side by side. That's a bit of a difficult thing to do. So I'm going to show you a little trick in this scenario. And every time we do these ones, okay, there's going to be little tricks to the trade. Okay, little tricks that you can do. So this is 10 elements in 10 positions. But if those two people, those two captains are going to be side by side, what you could do instead is you could pretend that the two captains, the CC, actually are one element. Okay, the two captains are one element. Okay, Captain A and Captain B, whatever. Okay, or first captain and second captain. If you pretend that they're one element, okay, kind of like people doing a piggyback, that would mean the two people go together, or you can visualize the two people in a three-legged race, if you've ever done one of those, where you tie the person, you have two people side by side, here's the two people, right? If you've never done a three-legged race, depending on where you're from, or if you've never been in a camp or something like that, what happens is you tie this leg together, okay? So they've got 1, 2, and then a combined third leg. But they're actually one set of individuals. They can't come apart. They're literally attached. And as a result, that's what we're doing here, is we're saying, well, if the captains have to be together, then let's attach them together, literally, physically. Okay? And if we do attach them together, then in essence, I don't have 10 elements anymore. Okay, when the captain and the captain become one element, okay, what happens is I go down from 10 elements to 9 elements. Now, this is exactly the same. We still have 8 other people. 1, 2, 3, 4, 5, 6, 7, 8. The non-captains, right? But now we have 1, 2, 3, 4, 5, 6, 7, 8, 9 people rather than having the 10. So those 2 people turn into 1 person. Okay, so now we have 9 elements in 9 positions. Okay, and if we have 9 elements in 9 positions, rather than being 10, 9, 8, 7, 6, all the way down to 2 and 1, 10 down to 1, 2 and 1, we go 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And what happens in that case is that 1 2-person superhuman, okay, is still one individual that can be arranged because they have to be stuck together. Now, this is a bit of a trick to do it, but in actual fact, that's what's happening. If I was to move the captains to somewhere else in the photo, maybe over here, okay, if I put the captains here, then that would be captain, captain. But if I put them here, that would be captain, captain. And if I go all the way down and put them in this spot, then that would be captain, captain. Okay? So anyway, that's how this is arranged. But we also have another consideration to keep in mind. These captains are different elements. So if I put captain 1 on the left and captain 2 on the right, they actually can arrange into 2 different positions as well. So my answer is going to be 9 factorial in this particular arrangement. But I'm also then going to have to flip it or times it by 2 because I can go captain 1, captain 2, or captain 2, captain 1. And so I just, I multiply them by 2 because there's 2 arrangements. I guess I could, this would be 9 factorial. And this would be 9 factorial, which is 2 times 9 factorial. Okay, and that's how we would do that type of a particular operation. Okay, it's a bit of a trick. It's a bit tricky. Okay, but again, I like to call this, gluing these 2 elements together, okay, to create one less element. And in this case, 9 factorial. 9 factorial. Yeah, I should know that off the top of my head. And then times 2. Okay, so that's going to be 7, 2, 5, 7, 6, 0. So that's how many different ways. Okay, so therefore 7, 2, 5, 7, 6, 0 is a number of pictures that these people could line up for where the 2 captains are side by side. Here's another thing that's a little bit similarly. Okay, let's say in this team, again, there's 10 elements, 10 positions, but in this case we have 3 sisters. Okay, and we want them to be side by side, because they're best buds, because they're pals. Okay, so as a result, again, it would be 10 elements. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But then what we would do is we would take the 3 sisters and we would combine them together into 1 element. Okay, so they become one super-duper large human being all tied together. Now, they're not tied together. They're just side by side. So they're kind of glued at the hip, if you want to think of it that way. 1, 2, 3, 4, 5, 6, 7. Okay, so we have 7 other people plus the 3 sisters. So then we go from 10 elements in 10 positions, we go into 8 elements in 8 positions. Okay, because 3 of those people become 1. They don't disappear and we go down to 7. 3 of those people become 1. So what we end up with is, again, 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And we're gluing them together, so that's going to be 8 factorial. But again, with the captains, remember we had captain 1 and captain 2, or captain 2 and captain 1. That's 2 arrangements. In this one, let's say the 3 sisters are A, B, C. We could have A, B, C. We could have A, C, B. We could have B, C, A, B, A, C, or C, A, B, C, B, A. That ends up being 6 different possibilities. And I don't want you to have to go and list these, because if we had 4 people together, there'd be a lot of things to list. So the little trick for this is there's 2 things that we're gluing together, so we times by 2. When there's 3 things we glue together, we times it by 3, but not then 2 then 1. We times it by 3 factorial. So when we have the 2 captains, there's 2 captains, so we times it by 2 factorial when we glue 2 things together. And when we glue 3 things together, we times it by 3 factorial. Again, another little trick. Okay? So I go 8 factorial and times that by 3 factorial. This may or may not work. I'm not quite sure. I think it'll work this way. And I get 241,999 920 ways. Okay? And so as a result, again, this is the whole idea of gluing people together. Okay? And it's a one strategy that we're going to see, and it would be one thing that would, people who are friends and stuff in a team will tend to kind of clump together. Well, if they clump together in a photo and they want to be side by side, that's the same thing as three sisters being together or two captains being together. We wanted to figure out the probability of any random photo happening that way. Then we would have 10 factorial, right? We would have the original example that we did, okay, which was 10 factorial. Okay, 10 elements and 10 positions. And then we would say to ourselves, okay, well, what's the probability of those three people who are pals being side by side? Well, of course, they choose to be side by side. So there's a lot less possibilities. 241,920. And if you remember, the 10 factorial possibility was, I think, in the 3 millions, 3.5 million. So we would use those two ideas to figure out the probability of having a picture where if those three people are together, not because it's a coincidence, but saying, oh yeah, those people are friends. That's why they're together. So the probability of that happening randomly is not very good. But the fact that it happened that way means that maybe something significant is happening, like those three people are friends. I also like to talk about a bit more nefarious things. So if you look at some, I don't know, let's say a private investigator is hired to find out if two people are having an affair. So they take photos at an office Christmas party, and at the office Christmas party, there's 10 people lining up for a photo, and those two people who are, they think are having an affair, they're side by side, and then they take another photo and they're side by side, and they take another photo and they're side by side, and then you start looking at the probabilities of those, and it's a pretty compelling argument for that private investigator to say, hey, these two people are maybe having an affair, even though we don't have any direct evidence of it yet. And I know that seems kind of nefarious, but we watch enough TV where stuff like that happens. So maybe that's a scenario where you could see where this would be useful. How many ways can a 10-person team, same 10 persons, so 10 people, 10 elements in 10 positions. Okay. 12 with the coach and the manager. So now we got our coach and our manager in there. Can't forget about the coach and the manager. They help out. They drive us to the game and maybe give us some pointers and stuff, as well as keep the water bottles full. They're important. How many ways can a 10-person team, 12 with the coach and manager, line up if the coach must be in the far left and the manager on the right? So now we have 12 elements in 12 positions. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. But we have a specific thing set out here. So it's not just going to be 12 factorial. That's what it would be if the coach and the manager could be anywhere in the photo, right? But what we're saying is, no. The coach and the manager aren't anywhere in the photo. Okay, the coach must be on the far left. So the coach has got to be here, and the manager has got to be here. So I put a little C and I put a little M there. And this is another strategy that we use when we're doing permutations. Because we know that the coach has to be there, there's only one person out of the 12 who can be there, the coach. Because the manager has to be there, there's only one person that can be there, the manager. That's it. All the other members of the team can jostle themselves amongst there. There's no rule that's saying that they have to be lined up in alphabetical order or by number on their back of their jersey or whatever it may be. So in this case, what happens is there's 10 people that can go in this spot. Not 12, because 1 and 1 have been taken out of the mix and have been put in definite positions. I call this fixing things in position. And in your notes, you'll find out, I talk about fixing a little bit nicer. So make sure you look at these notes, the good copy notes, and you say to yourself, okay, yeah, I can see Mr. Henley's description of what it is, as well as the words that he said in the video. So I fix them in place, which means there's only one possibility and one possibility. And then for everybody else, the rest of the team, they can line up however they want. And remember, they're all lining up, coach, player. So coach and player 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 and the manager. They're all lining up, so we multiply them all together. So it ends up being 1 times 10 factorial times 1, which is, we don't even have to times it by 1, right? Which just ends up being 10 factorial. Okay, so now when the coach and the manager are set up in that, and that's often the way the team photos are done, right? The coach and the manager are kind of on the outside, and the players are all in the center as the focal point, because they're the ones who win the games, right? They're the ones who play. They're the ones who are participating, but we still, of course, want to make sure that the coach still gets in the photo, because they were still part of it, and also the manager, they still need to be in there too. Okay, so as a result of that, Those are different ways and strategies and situations we can come across when we're doing permutations. Okay, so hopefully you see that as a little bit simpler. Now, so far we've been going the same number of elements and the same number of positions. But sometimes that doesn't happen that way. Okay, sometimes it's not so simple. So let's say we do a situation where we have a teacher and you've got 30 people in the classroom, and the teacher has to get, I don't know, let's say you're giving presentations and they're 10-minute presentations, and so you can only get 6 presentations in a class. Okay, so the teacher picks 6 people out of the 30 to go ahead and present that day. Well, then you're taking 30 elements and you're putting them into 6 positions: first, second, third, fourth, fifth, sixth presentation. Okay, and that's a different story. And as a result of it being that different story, then we have to be able to create situations like that too. So permutations do not always consist of the same number of elements as positions. Logically, accounting principles should include a technique where there are many elements in a set and a smaller group or a smaller subset is chosen and placed in some order. In other words, R can be equal to N, like here, 12 elements, 12 positions, N and R. 10 elements, 10 positions, 10N, 10R. Okay? Same idea here. Or even 8 and 8 and 9 and 9. But we can also have a situation where R can quite often be smaller than N. R can never be more than N. You can't have more positions than people. Otherwise, the positions don't exist because they're not being filled. You have to have more people or elements than you have positions. Okay, so let's go back for this scenario here. Volleyball. Okay, we've got the same team of 10, so we have 10 elements. Okay, but of course, those of you guys who know volleyball, you only have 6 people on a court at a time. So you have 6 positions. And those are the people who are playing. Obviously, some people are on the bench, and I know there's a rotation and stuff like that. But let's ignore that sort of stuff, and let's just put people for a starting lineup. Okay, so how do we do it? Well, again, we've got 10 elements. If position number 1 is what the coach starts with, then there's 10 people who can go in that spot. And then 9, and then 8, and then 7, and then 6, and then 5. And of course, he's got to pick a lineup with first position, and second position, and third position, and fourth position, and fifth position, and sixth position. So you multiply all those together. Now we can do that 10 times 9 times 8 times 7 times 6 times 5 on our calculator. That's easy for us to do. Okay, and I guess we could do it. 10 times 9 times 8 times 7 times 6 times 5 equals, okay, 151,200. But of course we don't want to have to do that all the time, especially if we have, I don't know, like, you know, a huge classroom, maybe all the grade 12s. You know, there's 100 grade 12s in your school, and we're, I don't know, lining up for a photo or something like that, and 10 people are getting in a photo in the prom, and there's, you know, 100 people at the prom. Well, that's going to be crazy, right? It's going to be 100 times 999 times 98. So we want to have a better way of doing this. And so what's that better way? Well, another way to solve the problem is to use the Npr formula for N elements and R positions. So rather than we have 10 elements and we have 6 positions, so we could just go, the number of ways is 10 elements, 10, that's the N. Remember, N is the number of elements, and R is the number of positions, so 10p6. And if we do the 10p6 in our calculator, we should come up with the same answer, right, if it's going to work for us. So 10, and then I use my NPR calculation, and then go 6. Now, not everybody's calculator is going to work the same, but of course you see 151, 200. Okay, but not everybody's calculator is going to be the same. Okay, so make sure you find out how to do that. Again, watch that little video on how to do permutations, because for something like this, it's, you know, it's going to be a pain in the butt eventually for you to do it. I'm going to do an example next where it's going to be a pain, and then even bigger pains. Okay, so let's look at another example. Of your 23 classmates, so we've got 23 elements. How many ways can 3 of them present their assignments? So 3 positions: first, second, and third. So again, if you map it out, you know, there are 3 positions: first, second, third. 23 elements, 22 elements, 21. If everybody has an equal chance of being chosen, the teacher's just randomly choosing students. Okay, then there you go. And it's not too difficult for you to go 23 times 22 times 21. Okay, remember, you're choosing first presentation and second presentation and third presentation as a total of choosing the 3 presentations. Okay, or we could write that as 23p3. Now 23p3 is a little bit easier. There's the P, there's the 3, and we get 10,626. So it's 10,626 ways for those students to present. Or you could go 23 times 22 times 21. Oops, sorry. Say this example. 23 times 22 times 21. Okay, 10, 6, 26. But again, when it starts to get longer, it starts to get a little bit of a pain in the butt. Okay, so we don't want to have to do that too often. Here's another scenario. You have a dozen assorted donuts. So you have 12 elements. They're assorted, so they're all different. No repeats. All a random combo pack, whatever you want to call it. Okay, now, how many ways could you eat 6 donuts? So I've got 6 positions in my mouth. Okay, or 6 positions, first, second, third, fourth, fifth, sixth donut that you eat. Eat 6 donuts if. So it normally would look like, if I'm just going to eat 6 donuts, 1, 2, 3, 4, 5, 6. But we must eat the jelly donut first. So if the jelly has to go first, we put a J for jelly here. We put a 1 here. Now it means that if the jelly donut has been taken out, then we don't have 12 elements anymore. The jelly donut's got to go first. So I take the jelly donut, I put it in number 1 spot. But I've got 11 donuts left. So I go 11, and then 10, and then 9, and then 8, and then 7, until I've eaten my 6 donuts and I'm full and probably bloated and feeling bad. Okay, but the whole point to all of that is I fixed one in place and then I've used my elements that are left. Okay, now this can just be multiplied out because again it's one jelly donut and then another donut and then another donut and then another donut and then another donut. Or you could use your calculator, 11 times 10 times 9 times 8 times 7. Okay, 55, let me make sure I got that right, 55,400. Or another way that you could do it, and this is a little trickier, is to go 11p5. And you're like, 11p5, wait a minute, we have 12 elements, 6 positions. Yes, but when we take the 1 out, the 12 elements drops down to 11 elements. And instead of having 6 positions, this position is already occupied, so then we have 5 positions. You could do it that way too if you want to. To be honest, I really don't care. Once we get to this setup, I know what you're doing. Okay, but you go ahead and figure out how you can calculate it. Okay, now here's another scenario. Same 12 elements, same 6 positions. But in this one, you must eat the jelly donut first and the chocolate dip last. So what do? 1, 2, 3, 4, 5, 6. We've got jelly first. It can only be the jelly. That's why I put a 1 in there. We've got chocolate dip last. It can only be chocolate dip because you save it till last because it's your favorite or whatever, or least favorite, who knows. And then that means that we no longer have 12 elements to juggle around here. We only have 10 elements because we've taken the jelly and the chocolate dip. Okay, so it's going to be 10 times 9 times 8 times 7. And I can go ahead and figure that out with my calculator if I want to. Or what I could do is realize that it's 1 times 10 elements in 4 positions, that little sort of thing that's going on there in the variable parts of donuts. Okay, if you want to, it's up to you. It depends on you. But once you get to this, I know what you're doing. You're going to get full marks. In many cases, I don't even look at the final answer. Okay, I just kind of look and say, oh yeah, they set it up right, so that's good. Okay, 8 times 7 equals. Okay, and 5,040 different ways to eat those donuts when you have 12 of them and you eat the jelly first, the chocolate dip last, and then from there. Okay, now what about if you have to eat the jelly donut directly after you eat the chocolate dip? Don't ask me why. Okay, so in other words, the jelly donut and the chocolate dip are kind of glued together. So we've got 12 elements in 6 positions. But in this case, 1, 2, 3, 4, 5, 6. What we're going to do is the jelly donut and the chocolate dip are right beside each other. It's kind of like having the 2 captains beside each other in the photo. You have to eat them one after the other. So they actually become one donut, a jelly chocolate dip donut. You could even jam them together and mash them together if you wanted to. Okay, which would mean that those 2 would become one, and then I'd have everybody else left over, the other 4 that I have to eat. Remember, the jelly and the chocolate dip occupy 2 spaces of the 6 that I'm eating, but now because I'm eating them side by side, I'm treating them as one super donut that's kind of mooshed together. Okay? Now, the reason why I'm gluing them together, but then making, rather than 12 elements, okay, I'm going to have 11 elements. Okay, because the chocolate dip and the jelly become an element. And then I'm going to have 5 positions. Okay, because they still occupy amount of space as a donut. And we're not literally smashing them together. We're just eating them right after each other. So putting them beside each other in the order. So in this case, I'm not fixing them in position because I don't have to eat them first. I just have to eat the jelly donut and then the chocolate dip after each other. Okay? Now, here I eat the jelly donut after you eat the chocolate. It doesn't say eat the jelly and the donut, jelly and the chocolate together. It says the jelly after the chocolate. So we're going to have a little bit of a variation on the theme here. Anyway, so I have 11 elements now, okay, including the jelly donut chocolate dip sort of combo, and then 10, and then 9, and then 8, and then 7. Okay. Now, usually what I would do is I would multiply that by 2 factorial, because I could go jelly, chocolate dip, or chocolate dip, jelly. But in this case, I have to eat the jelly after I eat the chocolate dip. So I don't multiply it by 2, because I can't go jelly, chocolate dip. I have to go chocolate dip, jelly. Okay. I eat the jelly directly after. Okay, so I can't go jelly, chocolate dip. I just go chocolate dip, jelly. So you're really going to times it by 1. And so then the number of ways is going to be, 11 P5 times 1, I suppose. Okay? Or again, you multiply all these values, 11 times 10 times 9 times 8 times 7. And there you have it, 5,040. So therefore, 5,040 ways. Okay. All right. So that being the case, then we move on. Okay. And we've still got a few more left to do. All right. And they're a bit tricky. So we've got lots of examples. And I want you to have lots of examples in order to do that. Okay. So in this case, how many ways can you arrange 8 people, okay, at a circular table? All right. Now this is a bit tricky. This is actually a very tricky one, and this is important because we sometimes arrange things in things rather than in a straight line. Okay. Well, if we arrange 8 people at a circular table, you can kind of think of the positions around the table: 1, 2, 3, 4, 5, 6, 7, 8. Okay. There's that 8 spots around the table. Now, logically, what you would say to yourself is the number of ways that I could do that for the 8 people is I could put person A here, and B here, and C, and D, and E, and F, and G, and H. And I have 8 elements in 8 positions at the table, okay? And so that's one arrangement that you could do. So in essence, when you're doing this, it's just sort of basically a permutation in a circle, okay? So there would be 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Okay. Now, as a result of that scenario, you say to yourself, well, okay, that kind of makes sense, I suppose. But when I do that, then I run into a bit of a problem. Okay. And the problem that you run into, you may not be able to see yet. Okay. 8 factorial is 8. Okay. 4,320. Okay. 4,320. Okay. So that being the case, then you're in that situation where it just seems like a simple answer. But the problem that you run into is this. If I have A and B and C and D and E and F and G and H, that's an arrangement around the table. If I rotate them and I put A here, and then I put B here, and then C here, and then D here, and then E here, and then F here, and then G here, and then H here, what you actually don't realize is this is exactly the same arrangement. You see how it goes A, B, C, D, E, F, G, H? And this goes A, B, C, D, E, F, G, H. In a line, those are exactly the same arrangements. Okay? Because I don't know where to start and I don't know where to finish because it's a circular table and a circle doesn't have a beginning and a circle doesn't have an end. So if you have no fixed frame of reference, this is what you have to do. Okay, so you have to realize, and of course I could juggle this one more and put A here and B, C, D, E, F, G, H, and so on and so on and so on. So there's actually a lot of repeats that I have in here. So the answer isn't 8 factorial. What happens is this. With this 8 factorial example, okay, it's correct. It just needs to be adjusted. Okay, and the adjustment that you have is created by the fact that we have a specific number of arrangements around a table. There are 8 positions that you can go around this table. So A could start here, or 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 here. So in fact, there's if it goes A, B, C, D, E, F, G, H, or A, B, C, D, E, F, G, H, or A, B, C, D, E, F, G, H, or even starting here, A, B, C, D, G, F, G, H, or A, B, C, D, E, F, G, H. They all go the same way. And so in actual fact, there's going to be 8 arrangements that are exactly the same. So the way that I can get rid of those arrangements is to divide them out. And if I divide them out, okay, then I find myself in that position or that situation where I don't have 8 factorial or 40,320. I have 40,320 divided by 8, which is 5040. And we're seeing that answer a lot, but that's just because it's 7 factorial. It's nothing crazy. Okay, so keeping that idea in mind, whenever I have a circular arrangement in the table, it's actually the number of people that create that circular arrangement. Okay, in fact, it's all based on the number of lines of symmetry that exist. Okay, and the number of lines of symmetry that exist in this table have to do with the number of elements around the circular table. Okay, another thing or another strategy that people use when they do this calculation is they say, okay, I've got 1, 2, 3, 4, 5, 6, 7, 8, sorry, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. I got to arrange these around the table nice and neatly. 6, 7, 8. Okay, so I've got these arrangements around here. What I do is I fix this one in position because then I know that this one has to be this one, and that's so the table can't rotate. And then I go 7, 6, 5, 4, 3, 2, 1, and I end up with 5,040 that way. Okay, which just doesn't make a difference one way or the other when you do it, but it sort of shows the idea. Now, the overall rule for this, and this is becoming really, really long. Okay, so the idea for a rectangular table is the same thing. You've got 10 people sitting in a rectangular table, so 10 elements in 10 positions, but it's around a rectangular table. So we would go, I don't know, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay? When you do a rectangular table, what you're going to find out is, oops, I didn't make it a rectangle, I made it a square. So if you're going to do a rectangular table, and then go 1, 2, 3, and then 1, 2, 3, 1, 2 there. Kind of like, when you're sitting around a fairly big table, dinner table, rectangular dinner table that a lot of people may eat at. Okay? When you're sitting in that scenario, well, this side is the same as this side, but this side is not the same as this side. Okay? So as a result, it's not that every seat is the same like for the circle. It means that every other seat is the same like it's a circle. So here we would have 10 elements in 10 positions, or 10 factorial, or 10p10. But then we would have to divide out by the number of identical arrangements that exist. And the number of identical arrangements that exist is, if A is here, or if A is here, that's the same. If A is here, or A is here, that's the same as if it goes alphabetically, A, B, C, D, E, F, G, H, I, J, all the way around. And so what ends up happening is we end up dividing it by 2 factorial, okay? Or 2, because there's 2 arrangements that are identical to each other. If we did a square table where all the sides were exactly the same, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, okay, then what we would have is well, this side, and this side, and this side, and this side. I know some have to be 2 and some have to be 3 and so on, but if you get the same 10 elements in 10 positions, we actually end up dividing it by 10 factorial, okay, or 10p10, 10 elements in 10 positions. We actually end up dividing it by 4. And the reason why we divide by 4 is when you look at these things, if the orders are the way that they are, now this is 10 elements, so it's a little bit quirky, and you can actually argue against it. But what ends up happening in the general rule is you would take n elements and n positions arranged around a table. So the number would be n factorial, n being the number of people who are positioned around the table in those positions. Okay, and we would divide by the number of lines of symmetry of the shape. Okay, the number of lines of symmetry. So for a rectangle has 1, 2 lines of symmetry. The diagonal line of symmetry isn't exactly symmetrical. Okay, whereas a square has 1, 2, 3, 4 lines of symmetry, so we divide by 4. How many lines of symmetry does a circle have? Well, a circle has an infinite number of lines of symmetry, but we don't take the n factorial and divide by infinity. If we have, it's 8 factorial, we divide by 8. If it was 10 elements seated around the table, then it would be 10 factorial divided by 10. Because each person actually creates a line of symmetry that exists. So in other words, when 8 people sit around a table, it's not a circle, it's actually an octagon. And when 10 people sit around a table, it's not a circle, it's a decagon. And when 4 people sit around a table, in this case, a circle would become a square if they sit around a circular table. Okay? And of course, we would 4 elements divided by 4. So that's the idea. Okay? So we take the number of lines of symmetry that are created. Okay, now, there's a bunch of questions here. Do your best with these. This homework actually may not be the same homework that you have assigned. Yeah, the homework that you actually have assigned from a different textbook is here. So this is the homework you're going to be doing, but lots of questions for you to do. Okay, lots of questions for you to do to help you out with that.